Hello. I'm happy to be here, and I'm going to talk about plants today. I have to say that yesterday, those of you who were here and who attended to the round table at the end of the day, you saw kind of my philosophical self. Today I'm here more in my scientific self. So my plan is to try to not to do many. I'm going to try to not to do big claims about whether plants have minds or they are intelligent or not. I'm more interested in showing you the kind of work we do. So I'm going to show you some cool videos, well, one cool video. And I'm going to try to explain why we are interested in plant movement and how it can help in general in our understanding of plants and in focusing in their behavior in a different way. To do so, I'm going to do nothing, it seems. Okay. To do so, first I'm going to talk about plant behavior in general. I'm going to give you two simple examples of plant communication and the fight or fly response. And you know, it is difficult to fight or fly if you are a plant. And then I'm going to focus on plant movement, and I'm going to explain our research we do at the University of Murcia in Spain. Then I'm going to talk about how this kind of research inform our understanding of plant minds, and I put minds between quotes, right? Because I want to talk a little bit about what I mean when I say mind. And in this process, we are going to talk about complexity and what that means and why we study behavior from the point of view of complexity. And at the end, I'm going to talk about a hot topic these days, plant sentience. And I'm going to just to mention a couple of ideas about it. So let's start talking about plant behavior. The first example of a well-known plant behavior I want to point out is communication between roots. This is an example of a set of experiments. This one is one of them, but there's a set of experiments developed by Novoplansky in Israel, and in which they show, or they claim to show, that there's some form of communication between the roots in plants. And how they do so? Let me explain you the experiment as fast and as simple as I can. The only thing you need to know as a previous knowledge here is that these small green holes that you see there that are open in one case and closed in the other case are stomas. The only thing you need to know is that stomas are that mechanism that you can use to measure plant stress. So when plants are happy, quote unquote, they are open. When plants are sad, they are closed. And happy and sad here means that if plant finds little water in the soil or some kind of toxic nutrient, then they close the stomas because that helps them to retain water and to be better. So happy plants open stomas, sad plants close stomas. Okay, so there you see a few pots, right? These blue and one orange cylinders there, and you see that plants are planted and their roots are split. And one part of them goes to one pot, and the other part goes to the other pot, right? And then the next plant shares one part of their roots with another plant, and the other part with the other one, right? So they are planted like doing little M's, right? So the orange pot you see there is an evil pot, as you can see because of the skull, and the bones there, right? It's a pot that basically lacked water. So the plant that has part of the roots there is sad, of course, right? That means has the stomas closed. Because the plant detects the lack of water there and then close the stomas. The cool thing is that the plant that shares the other pot with the first one also closes the stomas. And the plant, the third plant, that is planted in two perfectly good pots and shares no roots with the first plant, also closes the stomas, as the last plant does too. However, the other plants that share no, let's say, connection whatsoever with the evil pot, they are happy. So it seems like, and the important thing here is that all of them are in the same room, right? So it seems there's no communication through air between plants, right? So it's only the plants that are somewhat connected, that means they are sharing a pot, with a plant that is sharing a pot with a plant that is in a bad pot, the ones that are sad, the ones that close the stomas. So you can ask, why the last plant, the plant that is in the far right there, why, if the plant is planted in two perfectly good pots, is closing the stomas? The hypothesis is that there has to be some form of communication in which the first plant, the plant that has part of its roots in the bad pot, is signaling the other plants, hey, look, we can expect a lack of water at some point. So be ready. And be ready means close the stomas. So this is an example of plant communication through roots. Another example, it's an experiment by Apple and Cockcroft. It was famous, I would say, a couple of or 3 years ago, in which the plant, in which they did the following experiments. When caterpillars eat the plants, they make some specific kind of sound and vibration. And so what they did is to put a little device there that makes the same sound and vibration, but without being eaten. Even though only with the sound, only with the vibration, the plant gets ready to fight. That means to release the chemicals that they use to stop the caterpillars from eating them, right? I mean, the plant cannot fly, right? They are planted, but they can fight. And they use different kind of signals to anticipate some situation. And this is something that animals do too, and that we do too, right? We anticipate several situations in our day-by-day life. So this is usually seen an example of animals in some sense predicting their future, and we can see an homologous example in plants. And these are only two examples. There are tons of them. There are more and more plant behaviors described. One issue with them, though, is anthropocentrism. We have been talking about it, right? We talk about plant communication, plant emotions, plant decision-making, plant reason. All of them are our behaviors, right? We do communicate, we do have emotions, most of us. We make decisions. And I mean, in one sense, it makes sense that we pick these behaviors as an example of having minds, because we can relate to them. We think we are able to exhibit these kind of behaviors because we do have minds. And also our sciences, both the plant sciences and the cognitive sciences, can relate to those behaviors too. We are used to study them. We think they happen inside us, and we think that there's some physiological means to explain them. That's what neuroscience does, right? But what if plants are behaving in ways that doesn't relate to our ways, right? Do plants need to make decisions? Maybe yes, but maybe no. And maybe they have super interesting behaviors that doesn't relate to our own, right? To our own behavior. So to avoid anthropocentrism, to some extent, at least, we should try to think about what behaviors plant exhibit, even though if they don't relate to ours. Or we can do something easier, which is what we did, something simpler. That is that we don't have to guess whether plants move or not. Plants move, right? This is not something internal that we need to infer, right? We need to infer whether a plant makes a decision, but we don't need to infer whether a plant moves because we can see it. So this can be a window to understand plant intelligence, if any, or plant minds, if any. And that's why we study plant movement. From what point of view, though? As I said, plants move a lot. We all have seen it. It's difficult to see the movement with a naked eye in many plants. It's not difficult to see the movement in Venus flytraps or in Mimosa pudica, right? It's more difficult to see the movement in other plants, but we have now technologies like time-lapse that allow us to see the movement with our senses. The key to try to understand plant movement in a way that can allow us to better understand plant cognition, plant minds, plant intelligence, is the way this movement develops in time. Why? Because we can think about two kinds of movement that we see every day. We see, for instance, stones falling. They move, but we don't think that's an intelligent one, right? Or we see ourselves, for instance, walking. And we think that this is the product of an intelligent behavior. I walk that way because I have a mind and I want to go there. So the question we asked is there a way that we can distinguish these two behaviors? Do we have the scientific means to study one and study the other and say, okay, this behavior is stone-like. This behavior has the signatures of falling stones, so we shouldn't attribute a mind to that. This other behavior has the signatures of people who walk. And then it is still compatible with the idea that the organisms that exhibit it might be a cognitive system. So to explain this, I'm going to use an example. But what we are doing here, properly speaking, is to study the complexity of the movement. Complexity is a mathematical term, is difficult to describe, is even more difficult to formalize. There are different definitions depending on whether you, for instance, work in statistical mechanics or in computer science. So, but what we do know in the behavioral sciences, in the cognitive sciences, in the sciences of the minds of human beings, is that our behavior shows the signatures of complexity, while the falling stones don't do it. So let me use a simple example to try to hint, to try to gesture to what this difference in complexity is. We are going to compare a metal ball falling with a metal head walking, okay? You all probably have heard, although it is a myth, we are not sure this happened, but you might have heard that Galileo wanted to disprove Aristotle about the falling of things. So he went up to the Pisa Tower with a metal ball and with a wooden ball, same size, and they let them fall. And so the story goes, the two of them fall at the same time because the mass doesn't affect to the falling, right? So the different densities between the two balls didn't affect. So how do you expect, focusing just in the metal ball, how do you expect the ball is going to fall in this kind of situation? You are probably going to expect something like this, right? Straight line, the principle of least action is going to wait, boom, right? If Galileo takes the ball, comes up again, and throws the ball from the same place, you would expect that it's going to fall like this, right? The same path. No variability at all, right? If he goes, takes the ball, comes back again, the same path, right? And of course, we are human beings. We cannot put the ball exactly in the same place, but if the place is not a close one, you will expect something similar, right? I think you get the idea here. The non-complex behavior of a ball falling can be described with pretty much no appeal to variability. You take the initial point, the last point, and it's always the same one. Of course, you can only think that if there's a little bit of wind, right, it might move. Maybe not the metal ball, right, because it's too heavy. But you expect that. Imagine a metalhead, who is me, and you can see there, who happen to live in a church, who wants to go to his job at the Rodman Institute, and has to walk through the city. So the first day, if I go there, I might get a path like that one, right? A typical path, a shorter one. The next day, even if I take the same route, my path is going to be similar but different at the same time, right? I start in the same place, I end up in the same place. There's kind of a general form that is the same one, but I don't take exactly the same path, like the ball that falls exactly through the same route, right? The third day, it's going to be, again, similar but different. And actually, there can be another day that I need to stop in two other different places, because I think one of them is a barber shop, which I'm not going to stop by, and the other one is a bakery, right? And you can still see that there's a general direction, right? And there's a general change in the direction in the middle there. But still, it's more different. If you focus in some specific parts, you don't turn in exactly the same time. You sometimes go slower. You sometimes go faster. Every one of your steps, it's slightly different, right? And again, right? So, this kind of movement is similar to the stone in one sense, right? There's an initial position, a final one, and there's a path. And the path is stable and unstable at the same time, right? It has kind of the same direction, it goes to the same thing, but it goes in a different way every time. And this is the best way you can describe conceptually complexity. Complexity is a sweet spot between pure predictability, so everything happens the same always, right? Like the falling stone, and pure randomness, that everything changes every time, right? So complexity is this sweet spot that combines variability and stability. It's a behavior, when a behavior is complex, you can say that it's a behavior that constantly changes to remain the same. It's a little bit paradoxical, and that's why it's difficult to explain, but the take-home message here is that non-complex behavior, like the falling stones, are always the same, have some specific signatures, right? You can see them and see how they are. And human behavior that we consider intelligent has these other ones. Human, animal, actually, one of the pinnacles, one of the main aspects of our behavior is that it is complex. Our walking is a complex thing. If we fall, it's not. So, our question about plant movement is plant movement more similar to a metal ball falling or to a metal head walking? One of these three metal heads is me when I was younger and cool. And why? Because if the movement of plants is more similar to a metal ball falling, we have no reason to think it might be an intelligent one. If it is more similar to a metal head walking, we have reason to think it can be an intelligent one. So let me show you a video of a climbing bean moving. What you are going to see here is a climbing bean in the center and a pole that is 30 centimeters away from the climbing bean. And you are going to see two cameras, one lateral and one zenithal one, right? So hopefully we can see, maybe it's too small here, but I'm going to see. Okay. So you are going to see a plant doing a movement that is called circumnotation. You can see, if you can see, I don't know, but let's try. There's a shot of the plant doing this, doing a circular movement there. I don't want to go too out of the cameras, but I'm gonna try to show you how the movement changes. It starts being a circle doing this, see? Right? And eventually, the plant is going to go back, and you can see how fishing starts. There's no circle anymore. It's like it's trying to fish the pole there, right? It's going back and going there. You can even feel the effort, right? See? And she gets there. The plant does that before touching the pole. And that's an interesting thing. There has to be some form of sensitivity towards the pole because the organization, the change in the organization of the movement happens before the plant touches the pole there. Of course, I have to say, and this is a caveat, the time lapse can be misguiding sometimes. Again, if I can play it again, I hope. Maybe. I'm going to tell you. Yes. The time lapse, as I said, you can even feel the effort. This can be an artifact of the time lapse itself, right? It's like we see it moving so fast that we have that feeling. Every round is about 3 hours. So the whole video, this video is cropped, but the whole video is 3 minutes, and it's for, I would say, 4 days. So it goes fast. But let us see, again, this at least suggestive video, right? There's going to be one more rotation. Now there's going to be a change of light because we have day and night, right? And then the plant is going to throw itself against the pole, right? So we have this kind of videos. We have a lot of them. And so we put the plant in a recording booth. The plant is there, a camera up. We control light, humidity, everything that has to be controlled, right? And we have 2 conditions. In one of these booths, the plants are with a pole, and in other ones, they are with no pole. Why? Because we wanted to know whether the presence of a pole, that is a relevant aspect of the environment for the plant, because they are climbing beings, they need to find some support to climb, affected their behavior, made their behavior more complex. Why? Because if we see that a relevant environmental aspect makes the behavior of the plant more complex, we can claim that the plant is, first, exhibiting complex behavior, which is good, right? As we have seen. Well, it's good if you want to do what I do. If not, you don't care, right? But it was super good for us. And then whether the plants are actually sensitive to these relevant environmental aspects, like we are, right? We are sensitive to some aspect. Maybe plants are sensitive to other ones. So yeah, we have a very similar experimental setup as the video you have seen. A better one, but yeah, the pole is 30 centimeters away from the plant, and we let me see, one more. We did a lot of math that I'm going to not to talk about. So we can talk about if you are interested afterwards, but you just have to trust my word in this case. I mean, I did the math, so if you are interested, we did some techniques that are called normal peak, acceleration, multi-scale sample entropy based on empirical mode decomposition, and I'm becoming more boring and more boring as I speak, right? So no, I'm not going to talk about that. What we found, though, is that movement of the plant is not very similar to the metal ball falling, and it's way more similar to the metal head. So we have published this in that paper you see down there. It's Raja Silva, Holgumi, and Calvo last year. It's called the Dynamics of Plant Nutation. It's in scientific reports. But yeah, I think we have empirical proof that the behavior of plants is complex as you expect the behavior of an organism that you think is a cognitive system. So maybe you can say, oh, if that's the case, plants have minds. Yes, but what do we mean by mind? We were talking yesterday that I take the mind to not to be a substance, but a kind of relation, right? It's a relation between an organism and an environment. So it's not about having the concept of pole, right? We shouldn't think, I mean, maybe, but we shouldn't think that the plant has the concept of pole and then says, let's go there, right? Why? We said anthropocentrism, right? We need to try to explore the movement, the behavior of the plant in their own relation with their environment, right? The pole might be irrelevant for us, but it's super relevant. So we have to try to explore their behavior and not assuming that if we talk about plant minds, we are saying that the plant is thinking about what I'm going to eat later, right? So when we talk about minds, we talk about what you have seen in that video of the plant. Right? The plant is self-organized, exhibits a flexible behavior, right? The plant is here, the pole is there, but you see different patterns. It seems to be goal-directed, right? It seems quite clearly to go towards the pole, right? So what we think we have shown is that at least in our experiment, and at least with those plants, they are able to organize their movement with regard to the meaningful / relevant / salient aspects of their environment. And this is what cognitive systems do. We identify relevant things, and we discard non-relevant things, and we behave accordingly. So in this sense, plants have minds. Are plants going to write books? I don't know. But plants exhibit the most basic capacity of minded beings to be able to organize your behavior with respect to the goals you have or the goals you find in your environment. And I think this is good not only if you are like me interested in plant intelligence, but it's good for sustainability too, because it's not only genes, right? It's not like we can have a better, more sustainable agriculture because we modify the genes of plants, but because if we understand how plants move, we can set up better environments for the way they grow, and it is going to be more efficient because we are going to be more productive with less environment, right? And it's going to be better for plants because we are going to, for plants from our point of view, of course, right? Because we are going to try to provide environments that fit their needs, right? This is everything I have to say about the way plants move. As I said, I didn't want to make very big claims. I wanted just to show that there are different ways to understand how plant moves, and there are the way we approach it, right? But, plant consciousness. I have to say some things about it, right? Because you can ask me, Vicente, what about plant sentience? Well, I think that from the point of view, as I said, I come today here as a scientist and not as a philosopher, although it's kind of the same. I think that the best approach here is that we don't know, and we don't know now, because it is difficult to know, right? Eva was pointing before that it is even difficult to attribute mental states or feeling to other people. We don't have a very good theory of consciousness, actually. And the more different an organism is, the more challenging it is for us to attribute sentience, right? It's likely easy with our dog, right? But if you think of a mussel, right? Well, you know, the mollusk, are they sentient? They have a nervous system for sure, but they don't behave as similar to us as that we can say that. So we don't know, but it is possible. I could say that in any case, we should again avoid anthropocentrism, because we should expect that whatever their consciousness, whatever their awareness, their sentience is, doesn't have to match ours, right? You can expect that it is going to be very difficult. Very different. Why? Because they have, just to point one thing, they have a completely different body. They don't locomote. You know, they have different experiences. If you are interested in this, we just published this year a special issue in the Journal of Consciousness Studies on plant sentience. If you want the detail, you can talk to me, and I can give you them. Biologists, psychologists, and philosophers, both in favor and against of the idea of plant sentience. So I think it's an interesting resource if you want to kind of be aware of the state of the art nowadays. So I just want to say we need a better understanding of plant behavior, and plant movement can help. I think it's fundamental for our relationship with plants, both for our knowledge of them, but also for our relationship with them in our ecological niche. And I think this is not only an academic enterprise, but a practical one, because we can have better environment for all of us. Thank you.